Okay, so we're going to take a look at example 5 on page 86 of the workbook. All right, and this is a type of question that I don't know if we've done directly before. Okay, it's going to spin things a little bit differently than what we've seen so far. Let's read this together. So they're giving us a matrix A sitting over here, and part A of this gives us a set beta 1 of 3 vectors and asks us, is that a basis for the null space of L of A? What's interesting about this question is we've done problems like this before, and you could look back at some of the examples that we did and actually find a basis for the null space of L of A. But what you'll discover is that you actually get a different set of vectors than what they're giving us here for beta 1. So could it be that this beta 1 is a different basis for the null space of L of A? That's the question that we're trying to answer here. Okay, and I'd like to see if I can convince you that this really is a basis for the null space of L of A, even though it doesn't match the standard basis, so to speak, that you would get if you use this the normal way that we do this. Okay, we're going to do this in a sequence of steps here. Okay, step 1. First thing that we need to ask is, are these 3 vectors that are in beta 1 even in the null space of L of A? Okay, so for convenience of notation, let's give those 3 vectors names. I'm going to call them U1, U2, and U3. And so we could check to see if those are in the null space of L of A by just taking the matrix A and multiplying by each of those 3 vectors one at a time and asking, do we get 0? Okay, that's going to answer the question as to whether beta 1 is a subset of the null space of L of A. Okay, and it turns out that the answer to that is yes. Okay, if you did that, took A and multiplied it by U1, U2, and U3, you can confirm by direct calculation that you do get the 0 vector. Okay, I'll leave that to you doing the algebra there. Okay, next question would be thinking about the properties that any basis has to have. So for beta 1 to have any chance of being a basis, it has to be linearly independent. So that would be our next question. Is beta 1 linearly independent? Okay, well, we know how to answer that question as well. Okay, we can do that by forming a matrix where U1, U2, and U3 are our columns. Okay, so that would be our starting point. And if we do matrix row operations here, what we're looking for are where the pivots are. Okay, and so this you can, again, either do by hand or maybe by a calculator to save some time. Okay, and after doing row operations, there's the reduce matrix that we wind up with. Notice where the pivot columns are. We have a pivot in every column in this case, which means that if you think of this as the coefficient matrix of a system, we don't have any free variables. That tells us that the columns of this matrix are linearly independent. Okay, so the answer to the question that we asked is yes. These row operations yield a pivot in every column. Okay, which again confirms that those columns are linearly independent. Okay. And so what's left to verify that beta 1 is a basis? Okay, well, you might remember that the other property besides linearly independent that a basis has to have is that they have to span the space that we're talking about. Okay, we could verify that directly, but the easier way is to think back to corollary 2a. Linear independence is enough if we have the right number of vectors. In other words, if we can figure out what the dimension of this null space of L of A is, and we discover that the dimension is 3, then beta 1 being linearly independent suffices. We don't need to do any more than that. All right, so our third and final question, thing that we need to confirm, does the number of vectors in beta 1 match the dimension of our space? Okay, if it does, we have a basis. Okay, and I claim that the answer to this last question is also yes. Okay, and to get started answering that, we could ask, what is the rank of our matrix? Okay, so I'm going to go back to the top of the page, the matrix. Okay, and notice where the pivot columns are. This matrix is already in echelon form. We talked about how the rank of the matrix is just the number of pivot positions that we have. So we can see that the rank of A is 2, and then use the dimension theorem to figure out what the dimension of n of L of A is. Okay, so I'm just going to write in what we said above. Rank of A is 2. Can be seen from the pivot positions that we circled. Okay, and here comes the calculation that's going to give us the dimension of the null space. Okay. Let me correct that. Okay, so the dimension of the null space is equal to 5. Okay, that's the number of columns in our matrix minus the rank of A. Okay, we just convinced ourselves that the rank of A is 2, and so we get 3, which just happens to agree with the number of vectors that we have in beta 1. Okay, so if we put 1, 2, and 3 together, we have proven that beta 1 is indeed a basis for the null space of L of A. Okay, and just as an exercise for you, just to see whether this made sense to you, I would encourage you to go back and see if you can do part B. It's asking you the same question that we just answered in part A, but with a different starting